Okay, so we're very happy to have
Thanks for the introduction. Sorry for making me say that. There are several terms in this title that we are going to spend some time explaining. Maybe even most of the talk is going to spend on explaining exactly what are these things we are discussing here. But let's start with maybe the easiest term to explain this title: algorithms. So the first thing we are going to talk about is algorithms, but more specifically, algorithms for restricted units. So in many different cases, we know how to solve problems in some complexity, but if we assume something about inputs, restricted inputs in some manner, then we can solve the algorithms much more, solve the problems much more quickly for these families of inputs. So you probably have more than enough examples in mind of such cases. Maybe two very popular families or classes of families for which you usually have faster algorithms of things like sparse inputs, which can mean anything starting from a small number of edges to things that are stronger than this, like bounded tree graphs or some structural type of sparseness. Planar, maybe even small tree width, and so on. Another family that we commonly have better algorithms for is random. So for a lot of problems, the average case complexity is lower than what we can show for the coarse case complexity. And our objective with this talk will try to be to present some unifying approach that's better algorithms for the restricted cases. Well, the family of restricted inputs we are going to have in mind is something we are calling almost regular inputs. So what are almost regular inputs? So for example, if you're talking about graphs, let's think about this as graphs in which the maximum degree is at most a constant times larger than the average. So this, for example, in the case of graphs, include bounded degree graphs because these are small, but certainly the maximum is a constant factor larger than the average. It would also include random graphs, some nodes, but mostly graphs that increase similarly. But it will also include many more things that are more general than this, or stronger than this, or you don't usually see that there are. For example, regular graphs of anything, like graphs of root n, it's still out almost regular in this sense. Something else that is almost regular in this sense is very dense. So if, for example, I have a graph with this epsilon, that's constant times and squared edges, then this is certainly almost regular. Why? Because the average degree is of size roughly n, but the maximum degree is also of course. And before we dive into exactly what are the results and exactly what are the tools, let's just give a couple of examples, somewhat informal results we are going to present, just to give you some taste of what we mean by this unifying approach or what we get from this. So an example for a statement we are going to get is that if you can solve k-sub in c to the n time for any constant c, then if I give you a case of formula that is dense, that has many clauses in some way, then you can solve k-sub for this type of formulas in c minus epsilon, where epsilon is some constant. So no matter what is your algorithm for general k-sub, you can get an exponential improvement for the case of almost, in this case, dense. Another example would be that solve maximum independent set is sometimes c to the n, then we can exponentially improve upon this again for something like almost regular. And both of these examples are kind of a black box results. So I don't assume anything about algorithm that solves this problem. I'm saying if there is some algorithm that runs in this time, then I can turn it into a faster algorithm for the more restricted family. inputs. We also have some white box results. So for example, for graph coloring, we will use the same techniques, but we will not get something that depends on an arbitrary algorithm, but we will actually need to do something about specific algorithms. Okay, and maybe let's say a few words about the type of problems I discussed so far. So the type of problems I discussed are exact algorithms for complete problems. So we mentioned maximum independence set, graph coloring, KSAT, all of these are complete problems. We don't believe that they have solutions. And actually what we believe, or at least the best thing we know for all of these problems, are exponential algorithms. And even though the algorithms are exponential, there are still non-trivial improvements there over very few things we can do. And this was in fact something we knew long before we had the definition of L. So in the early 60s, for example, Eld and Karp already published non-trivial algorithms for the traveling sales. Before we defined what L is. Afterwards, we started having a very, very large algorithms around this type of things. I will also give you a few reasonings that we care about this type of problems, both classical reasons and some newer ones. Classically, people cared about things for perhaps mainly these two reasons. First of all, the fact that the problems and the R didn't solve it. So problems needed solutions anyway. And the other thing was that from a theoretical point of view, we know very, very little about hardness and complexity of problems. For example, we don't even know that SAT doesn't have a linear solution, time solution. So understanding anything more about what makes this problems hard, or which cases that are hard or something like that. But a newer reason that popped up in the last 5 years or so is that people started taking conjectures about these running times, running times of exact exponential problems, and assuming these conjectures based a lot of conditional lower bounds for polynomial time. So we're not going to dive deeply into that in this talk, but if you ever saw the term SETH or strong exponential time hypothesis and all of the fine-grained complexity field and things like this, then it became very common to assume these conjectures about the running time type of problems and deduce some polynomial lower bounds based upon that. So there's some newfound interest in exponential running times. And maybe something else that I would mention is that arguably the biggest, or one of the biggest open problems in cryptography since forever was to base cryptographic elements on empty versus V conjectures. And one roadblock on the way to doing that is the fact that we don't have our distributions for empty problems. Like we don't have any distribution for which we know, say, that if you could solve this empty complete problem of this distribution, then we could solve the problem. This is NPR to solve the problem of this distribution. So in some sense, our results imply that natural or symmetric distributions have inherent reasons to not be as hard as the ones. So it doesn't mean that they are not hard to follow, still exponential, but it does give us some explanation for why usually whenever people get these ideas for natural distributions that they think should be hard for some empty-complete problem, sometimes afterwards people get a better algorithm for this distribution. Okay, so the way we are going to spend the rest of the talk is mostly to explain which tools are we using, because this is the main thing I want to get out of this talk with. Afterwards, we'll also state all of the results we're getting. Most of the focus is going to be on this. And the main tool we are using is something called the Hypergraph Container Method. So next, we are going to explain what exactly is that. So the Hypergraph Container Method is a very powerful tool in mostly combinatroics. It is somewhat recent. This was discovered independently by Saxton and Thomason and by Balogh, and Samotij, I think. this is based on a basic approach that appeared much earlier for graphs instead of hypergraphs. This is dating back to, I think, something that could be considered that appeared in the 80s by Lightman and Winston, then more recently in the early 2000s by Sapozhenko. And the newer thing, the 2015 thing, is basically a generalization of this from graphs to hypergraphs. And since then it was used very, very extensively. So it was used a lot in extremal combinatorics, extremal graph theory, so some applications in additive combinatorics and more. And basically, what this method does is to characterize the structure of independent sets in hypergraphs that behave nicely. So we'll try to define what exactly does it behave nicely, but the type of statement we are going to want to use the type of statement that is something like, if an hypergraph H satisfies some conditions, again, let's not care about which conditions for a second, then every independent set hypergraph, what is an independent set? This is the subset of vertices that doesn't contain a full edge. So every independent set in the hypergraph is fully contained in one of a small set of containers, small family of containers. What is containers? Containers are just subsets of the graph vertices that are not going to be very large. They're not going to be very small, but let's say that they're going to be somewhat small. So we're going to have this collection. It is not collection that is quite small of subsets of containers that are not that large, and every independent set is going to be fully contained in one. So let's write something that looks almost formal, even though it's about as informal as the last slide. So the type of statement we're going to show is something like, if H is a nice enough hypergraph, then there exists a bunch of subsets. We're going to call these subsets containers, C1 to CR, that are subsets of the vertices of the hypergraph, such that the number of containers is small. Each container by itself is not very large. So they're not very large, and the size is almost 1 minus epsilon times the number of vertices of the hypergraph, where epsilon is a constant. So it doesn't depend on n or 3 or that. And the reason for which they're called containers is that we are going to say that each independent set in the hypergraph is fully contained in at least one place. And so they'll contain all of the independent sets. And let's see some drawing. This drawing is for graphs and not hypergraphs, because my artistic skills are limited. Time is finite. So this is a graph. These blocks are containers. They are just subsets of vertices. There are not many of them. This is a small number. And each container by itself is not very large. It doesn't cover all of the graphs. It covers one constant fraction of vertices in the graph. And what we will say is that whenever we have an independent set, for example, these 3 black vertices, then the independent set must be fully contained in one of the containers, in this case, and what is left for us to do is to define exactly what does small mean, what does nice mean, and so on. So to do that, let's talk about graphs, not about hypergraphs. The definition for hypergraphs would be quite cumbersome, so let's restrict ourselves to the basic version for standard. So for graphs, what exactly this means is the following. Let's say we have a graph with n vertices. Its average degree is d, and its maximum degree is at most c times d. So think of d as something that can be completely arbitrary, but c is a constant. So this is basically what we called almost before. In that case, we have containers as before. And now the meaning of small is going to be that the number of containers R is 2 to the little o of n, but this little o is with respect to d. What do I mean by that? I mean by that as d grows, then this thing over n vanishes. Meaning, for example, that for every epsilon, there is a large enough d such that for every d larger than this, the number of containers will be at most 2 the epsilon. Right, so this little o n sub d means that this over n goes to 0 when d goes. And this epsilon bounding the size of the containers is a constant that only depends on this c. So if this c, if this gap between the average and the maximum degree is a constant, a real constant, and this epsilon is a real constant as well. Again, doesn't depend on d, doesn't depend on. Okay, and this is the basic statement for graphs, but actually we are going to show that you can get a bit more out of it. And this is something that is implied by the statement. You can actually also assume that if you look at each container, which starts at the vertices, and you look at the induced subgraph on the container, so every edge that is fully contained inside this subset of vertices, then it is sparse. There aren't many edges. H here is G. Yes, so it's oh, yeah. That's good. So H is G. This is the lesson. Yes. So H is G, and this is the same statement as before, but we are adding this red part saying that not only the containers are not very large, but also the containers are sparse, since there aren't many edges per container. Why is that true? I mean, why can we show that the original version applies this version? The reason is that if I just use the original version and we got now I see a container that still has many edges, has more than epsilon. Notice that dn is basically the number of edges. So if a container still has a constant fraction of the number of edges, then actually the average degree didn't change very much. The average degree is still roughly the same as it was before. There's a most factor epsilon difference. So this means that the graph is still almost regular. So I could use the container method. And
but actually, it's a proof.
yes, the proof will give it automatically, but so this is also true for the hypergraph case and everything, just because generally having this property means that you can do it again and again. We are not going to do the math, but because the containers get smaller in a way that is not negligible, the number of containers you get by just doing this as long as you can doesn't go up. So again, let's not do the math, but good. So epsilon c is a constant, which depends only on this like gap. Not on d, not on. It depends also on the uniform.
Today. Okay, let's see.
So the thing is, like the important point you are pointing out is that this small thing was small when d grows. So this means that if d is small, it would be that the number of containers is everything. Not small.
But let's say there are no edges, no edges.
Okay, actually, this is a very good point. What we are very soon going to see is that as long as this is not the case, as long as the graph is not empty, if the result is one, then you can't have dependencies that are large. But yeah, it's a good point. We should say something about the graph is not empty. It's not zero.
Okay, but let's just say D is more. R is like R is.
R is large.
R is.
Yes. So you can imagine here something like maybe for simplicity, let's call this 2 to the n over it. So this is not exactly but always. Think of it as small as 2 to the n over it. Okay, and actually the reason that this red part is interesting is that using the red part, a lot of times you can actually get better bounds on the sizes of it. Right, so let's see, okay, something I want also to mention is that this delta here is we also think of this as a constant and it would affect both epsilon and this small thing, but as long as delta is a constant, then let's take okay,
And now I'm going to show you why this new condition actually helps us get better bounds on the first size. So let's see an example of something called supersaturation for regular graphs. So let's say that I have a graph, not an hypergraph, is fully regular, meaning that exactly all the values are, let's say. Then first statement that we want to show, again going back to your question, is that if G is irregular and D is at least 1, then every independent set is of size at most half of the number of vertices. Why is this true? This is true because consider the cut between the independent set and the rest of the graph. The independent set is D times the size of the independent set edges touching it. It's an independent set, so all of them cross the cut, they can go inside. Which means that all of them need to find a place somewhere on the other side of the cut. But the other side of the cut is only D times the other size of the other part of the cut edges. Touching. This is the sum of the. This means that D times whatever is out of the independent set must be larger than at least as large as D times the independent set. Giving an independent set most size. And what's called supersaturation is showing that if you have some structure that is bounded in size, that if you have anything that is slightly larger than this, then you would actually get a lot of okay, maybe let's phrase it more specifically. What we are going to show is that if I have a subset of vertices that is much larger than this upper bound on the size of independent sets, then it will actually contain a lot of edges. A lot of edges in the subset. So if I have a deregular graph and I have a subset of vertices of size half plus delta times n, then the induced subgraph on this subset of vertices d prime is going to have at least delta times dn, which is delta times number of edges in the more or less. And why is that so? This is true for exactly the same case. I look at the edges touching all vertices of B prime, remove everything that can go to the other side, and whatever was not removed must be left inside. Right, so again, we are not doing the math to avoid ugly calculations as much as possible, but what is the implication of this? The implication is that if I have a subset of vertices and I know that the induced subgraph point is sparse, actually it must be small. Right? Because if it wasn't small, if it was size half plus delta, then the number of edges would also be large. So this means that by taking this statement and applying it for regular graphs, for example, we can actually get that each container is of size half plus epsilon. Epsilon is a small yeah, so before it was 1 minus epsilon.
In C now is 1.
So yeah, as Noga is stressing, it is half not in general, but specifically for regular graphs. Why is it half for specifically regular graphs? Because for regular graphs, we showed that if you are sparse, you are of size half. But the same form of argument will also go for other graphs, but it will also always go for saying that if you are sparse, it must be small. Small will depend on the. Okay, so for example, something that is implied, and actually it was known before, but it's implied the tighter bound is that the number of independent sets in a deregular graph, and let's say D is very large, is roughly 2 to the n over. The number of independent sets in general. Why is that? The reason that this is implied is that we just take a union bound over all containers. The number of containers is small. This is the little n. And in every container, which is of size roughly up, we just take all subsets over the system. So this is what we meant at first, saying that this container method basically characterizes the structure of independent sets. We are showing that the independent sets are clustered in some non-trivial fashion, which means, for example, that there can be many. And the same here, I'm going to only say something very, very quickly, just for completeness. But the same thing we did here, if we do it in larger uniform hypergraphs, helps us also say statements about the number of graphs not containing some subgraph. So, for example, if I would look at the hypergraph I get by as vertices taking all of the possible edges of the complete graph on n vertices, and then I would add an hyper edge with 3 vertices for everything corresponding to a triangle, for every 3 edges that are a triangle. The now independent sets in this hypergraph are exactly the edges of triangles 3 graphs. So the same type of argument from an hypergraph of Informally can be used to bound the number of triangle graphs. So one type of question is that, so a lot of applications using the hypergraph container methods, the method is saying something like, what is the number of graphs that don't contain some edge, some size. Okay, so this is what I wanted to say about the statement container lemma itself. And now let's see a very, very simple application. So something I didn't tell you, but we should say is that also getting these containers can be done. So given a graph, if I want to generate the containers, I can actually do this in time is roughly the number I'm getting. And now let's see a very simple algorithmic application of this. And the problem we are going to have this application for is maximum independence. So that is maximum independence set. I give you a graph. I want you to tell me what is the independence set of maximum stuff. So given what we just saw, it is a trivial suggestion for an algorithm. Let's just compute these containers, enumerate over them, go over the containers one by one. And in each container, we are going to look at the induced subgraph on the container and solve maximum independence set on this subgraph, which is smaller. So this is going to be quick. So the first thing we need to note is that this works. This would actually find the maximum independence set in the graph. Why is that? Someone should answer. Great. So the maximum independent set is an independent set. So it is contained fully in one of the containers. So in one of the parts we define it. Another thing to note is that an independent set in an induced subgraph is also an independent set in the graph. So we also don't find something large. Yes. Yes. So what I just noted, but I didn't prove or show in the slide, that we can also show that we can also do this. So also for the higher uniformity in general, we can also produce I would note though that from the standard statement to the second type of statement, this was algorithmic given the way we described it, but also the first statement. Yes. So in the container part, we might want to do the container thing relatively, we want small containers or else. But let's say that we now have this black box where something takes the graph and computes the containers for us. And now what we are going to do is just take the graph, compute the containers, and then for each graph, for one time, just solve maximum independence set and this container. Okay, and how much time is this going to take? This is going to take the number of containers times whatever it takes to solve maximum independence set. Let's say this is n. But on a graph, this doesn't have a lot of vertices now. So for example, if we have done this thing for regular graphs, then now if maximum independent set takes C to the n time, this would only take roughly C to the n over 2. Because each of these containers is of size roughly n over 2. So this implies, for example, that if maximum independent set is in C to the n time, then regular maximum independent set with infinity takes C to the half plus little o 1 based on D. And this means that if D is large, then we have much better algorithm. Recursively for what? So the containers themselves will be now certainly not be fully regular, but also they will be. So there are actually a few things that go on, even if the regular degrees are getting smaller. Here we do have some. So this thing gets smaller as the degrees get larger, but of course there are stops.
Maybe.
Good. Okay, which leads us to the second point in this recipe we are presenting you for better algorithms for regular or almost regular instances, is that in many problems we are going to also have an algorithm that is better in the case that the degrees are bounded. So in general, what we are going to do is use this approach with containers, get better algorithm in the case that things are almost regular and the degree is large. You consume the large to get something. But if the degree is small, meaning that it is bounded by some constant, the constant we need to pass for the little o of 1 the small count, below this constant, we will just use an alternative algorithm for the small in this case. So this is the general recipe we are going to try to follow to start with results. And what we are going to do next is to try to go over which types of results we are actually getting. And the first one would be for graph coloring. So a quick reminder, what is graph coloring? A graph is k-colorable if we can color its vertices with k-color, meaning assign a number, let's say, between 1 and 10 each vertex, such that no edge is monochromatic. So whenever two vertices are connected by an edge, we couldn't have assigned the same color to both of the vertices. So a graph is k-colorable if there exists a color with k colors, and the chromatic number of the graph is the minimum k. Okay, and this is as we like in all of the problems in this talk and complete. And this was known almost as early as and it was known also at the same time. It was not even just deciding whether something is k color. This is then complete for every k is at least 3. So saying whether or not a graph is 2 colorable or part is easy, but for every k it's really loud and complete. And if we are trying to actually solve this, and we will try the first thing that comes to mind, then the solution is going to take k to the n time. Right? If I want to decide whether or not I can color some colors, the naive thing to do would be to just try all k colorings of the graphs. This will take me k to the n time. This goes with k. So, for example, for computing a command, quite bad. But in fact, we don't need this dependence on so very early on, in 76, Balogh suggested a very simple dynamic programming algorithm that uses the chromatic number of the graph in 3 to 10, regardless of what the chromatic number is, regardless of k. And the reason we are mentioning this is that this is built upon a very simple but very important for us observation, which is that a graph is k-colorable is exactly the same as saying that the vertices of the graph can be partitioned to k-independent sets. Right? Because every color class is an independent set, it doesn't contain any edge because this would be edge. But also, if you have a partition of the vertices to k dependencies, then you just color. So this means that the question of deciding whether or not something is colorable is the same as the question of deciding to how many independent sets I can partition the vertices. Okay, and this led to this very, very simple dynamic programming algorithm running time 3 p.m. So this would just be, we're going to compute the chromatic number of the induced graph on any subset of vertices. We're going to compute this for all subsets of vertices. So we're going to pass over all subsets on increasing size, or not the decreasing size, from the smallest, slightly larger, and so on. And whenever we have a subset we want to compute this chromatic number, we're just going to take the minimum over all independent sets inside this subgraph of 1, which is the independent set, plus the chromatic number of the rest, which is smallest. So we already computed one of that part. Unless the entire thing is independent set. So just there's probably no reason to go over this that much. We're not going to use it. This is just a note, but this runs in time 3 to the n. It's just go over all subsets, and each subset go over all of the subsets. And this was improved many, many, many times. So it was improved in many different ways. It was first improved by saying maybe let's not consider all independent sets in the subgraph, but only maximal ones, and then you get something, so on and so on. And finally, in 2009, Balogh et al. Obtained an algorithm that runs in 2 p.m. There's something people conjectured should be the best possible purpose. It doesn't have a very. Oh, that's a good question. Whenever I'm writing O star of something, I mean that I don't care about polynomials. This is the equivalent of this is the O tilde of a big. Yes, so this means that there's some polynomial data. Just deciding it's negligible because polynomial stuff are like so less. Okay, good. So finally, people obtained 2 to the n algorithm, which for some reasons it's best possible. And this is for computing the chromatic number, general problem. The question is, can you do better if you just want to decide a parallelity for some small? So for k, which is at most 6, we do know we can get some exponential improvement over 2 to the n, and even this requires some problems. Like for 3 coloring, this is by Beagle and Epstein, then for 4 coloring, then for 5 and 6 coloring. It's more recent, but for every k which is larger than 6, we don't know currently if we can solve k coloring faster, exponentially faster, then we can compute the chromatic number in general. Something we do know, which is also somewhat recent, is that we can compute the chromatic number faster if the graph is somewhat sparse.
When you say that, can you shave it?
No, so this is just compared to the general here.
But not for everyone.
No, this is just comparison. This is what I meant like a white. I mean, people believe that we shouldn't get general values faster at the end, but maybe and was clear. Okay. Yeah. Okay, something else that we do know, or somewhat recently, is that if graphs are somewhat sparse, then we can compute the chromatic number quicker. Somewhat sparse means that they have at least a constant fraction of vertices, degrees bounded by a constant. But let's not care about this more general statement and just state the following corollary. We can compute the chromatic number in 2 minus epsilon to the n time for graphs in which the degrees are bounded by delta. This epsilon only depends on this delta. So for every constant bounded degrees you're going to give me, there is an exponential improvement. for complete programmatic, which is great for us because, as we said before, this is exactly the type of statements we are going to need to balance out what we get from the containers for hypergraphs. That's so like the way we're going to once again use this containers recipe is to say, if we have a graph that is almost regular, then either the degrees are large enough for the number of containers to be small, and then we can use the containers, or the degrees are bounded by some constant, but it doesn't matter how large this constant is, because as long as the degrees are bounded by a constant, I have a better algorithm. Right, so this is the type of thing we are going to use. And the statement we do get is, as maybe I just implied, is that for every k and c, think of it as two constants, you can solve k coloring in 2 minus epsilon to the nth time, as long as the maximum degree is at most c times the average. So for every constant k and every constant c, I have an exponentially better algorithm for k coloring, as long as I have this c gap between the maximum and average. So once again, as before, this includes regular graphs of any degree. This includes all graphs that are dense, all graphs with at least epsilon edges are also included.
Computing also regular graph with speed.
Yes, so we don't know.
Yeah, it's regular to compute with speed.
Oh, what do you mean by that?
Computing is regular.
Side,
That's a degree of regularity.
and you want to compute coloring and not just.
No, to find.
Oh, yes. And we also need to assume that k is a constant. So, yeah, what Noga is saying is that I assume that k is a constant as well. So if k is a constant, let's say the graph is regular, I get an exponential improvement, but I don't get an exponential improvement for computing, which is, I mean, I don't know if it's a good thing or a bad thing, but people do assume that the 2 to the n is the best thing we should be able to do for general graphs. If it was not true for regular or almost regular graphs, I wouldn't. But maybe it's not. But if what people believe for various reasons is good, then it makes sense for general, for a large page, to get improvements for something like this. Okay. The problem we are going to face when we will try to use containers for this is that soon we will see the container statement again, just to get reminded of what it said. But the container statement said something about one. It said that every independent set is contained in a container. But now, when we're talking about colorings, we're going to care about several independent sets at the same time. We're going to have k independent sets we care about, and we need to say something about all of them at the same time, which is not something we usually do. And the way we're going to solve this is we present some generalization of containers for both graphs and hypergraphs, actually something called partition containers that would let us control several independent sets at the same time. So this was the container method in the formal statement. I just have containers, the number is small, each container is somewhat small, each independent set is contained in a container. And I'm not going to prove anything, I will just state, again, informally, what is this partition containers we are presenting. So they are very similar. They're still saying under the same conditions, if I have an hypergraph satisfying this and that conditions and get containers, their number is small, each of them is not very large. But now, instead of just saying that each independent set is contained in the container, we're going to say that each small collection, so k is a constant again, each small collection of k independent sets can be partitioned into two parts. So I have k independent sets, I can partition them to I independent sets and to k minus I sets, such that all of the independent sets of the first part are contained in the same container, and all of the independent sets on the second part are contained in the same container. which is enough for our results. I'm not explaining why, but also this is somewhat the best you can hope. The reason you couldn't go for one independent set is if, for example, your graph is let's say completely graph, then you might have two independent sets of algorithmic. So you can't go for every two independent sets to be fully connected. But we show that this is in a sense the worst. So if there's a lot of independent sets, they will always have a partition of 2. And this is without explaining, oh, this is the crucial technique. This, I mean, like, if K is 1, then this just means that in partition 1 container. This means that not only that each independent set individually in one container, but also collection can be extensive. Okay, and for the last few minutes, what we are going to say is just state the second part of the result, which is for K side. Very quick reminder: K side is getting a KCNF formula. This is a Boolean formula with CNF form and closest size of K. If you don't remember what it is, and we need to decide whether or not this is fine. The best known algorithm still takes 2 to the n time. Now this star is actually hiding things in the other direction. So there are very clever ways to shave even slightly more. There are ways to shave things out of this 2 to the n, but there is no way that we know of to shave something exponential of the n. And people strongly believe that we shouldn't be able. So this is strong exponential hypothesis. Soon, you can't watch it 2 steps generally. But here, for every constant K, we do have an improvement, exponential improvement. So for every constant K, we do know how to get 2 minus epsilon sub K to the n. For some epsilon, it would be a positive constant as long as K is constant. And yes. Maybe I'll just say it again, sat in general, not assuming anything about this. They have to be not of constant size. So 3 sets, for example, can be solved in like 1.3. When we talked earlier about this only works for a constant, it comes from the fact that the process of constant size, and in a sense you have some information that is very small and that's just going to follow this information. Clearly always very good. But you are right about it, because some of the epsilons are small. Like when we talked about expose myself, when we talked about the 6 coloring algorithm, epsilon is something like 10 minus sun. Epsilons can be very large elements. Okay. So stat in general takes 2 to the n, K stat for every constant K, exponentially faster. Something called the K-stat Sparsification Lemma. It's a hugely celebrated result. It's a very famous thing. People do it also in all of these SEH law bounds, but in many other papers. Is the following statement. This is by Pagliazzo from 2001. They show that for every K and epsilon is positive, slightly positive. Any case of formula on n variables can be written as the disjunction of 2 to the epsilon n, which is the epsilon it shows. This is a very small formulas, such that each formula is still on the same number of variables, but it is very sparse. meaning that in each of these formulas, we can reduce any case of formula to a very small number of formulas that are each on the same number of variables, but have only a constant times n clauses. The number of clauses in each formula would be a constant times the number of variables. So with less words, this just means that k-sub can be reduced to sparse k-sub. You can always take k-sub instance and make it sparse. Again, with a footnote, we don't exactly be one k-sub instance, but this junction of a very small amount of k-sub instances. But it does mean, for example, that if you have a faster algorithm for sparse k-sub instances, you would have a sparse algorithm. You have a better algorithm. Sparse meaning that the number of clauses is some constant times the number of variables. Good. Yeah, so your sparse means the. So you pick epsilon, and the constant is going to depend. The constant in the sparse is going to depend on this epsilon you pick. And now the number of formulas you're getting is due to the epsilon. So you can pick epsilon as, yes, you can pick epsilon as small as you can. I mean, few in the sense that again, if I add an exponentially faster algorithm, slightly for sparse formulas, then I could pick the epsilon small enough that and so this is usually used to say that in that sense, in the sense of time to exponential improvements, sparse k-sub is our general. And our result is a complementing statement. What we are saying is that if k-sub can be solved in C to the n time, then k-sub for formulas that contain at least some large constant times n clauses, and then there is a note here that we will soon get to, can be solved in C minus epsilon. Right, so there is a large enough constant such that if you have enough clauses, you can solve it more quickly. But the footnote I should mention is that it's not enough to have just this many clauses. They also need to be well spread. In one sense, in the sense that, for example, it will not help us. If you have the same clause a lot of times, it's not helpful. If you have like root n variables that have n to the k over 2 clauses, it's not helpful. So we need something about the clauses being spread out. The definition is a bit cumbersome, but I will just say a few things that do follow this definition. So, for example, if you have C and clauses that are distributed randomly, this is fine. And maybe something else that is important. Example of this is that any epsilon, which is a constant times n to the k clauses, must be well spread in that sense. Because if you have very dense formula, then you can't really have all of the clauses in the same way. Spread. So, for example, this implies that without any extra conditions, if you have k-sub that is an epsilon fraction of how many clauses you can possibly have, then it can be solved exponentially faster than general case. But we actually don't need that type of density, we just need the large constant times n, plus something that I will not get into about how well spread they are. Okay, quick summary of what we were saying. So we're presenting this powerful tool from extremal combinatroics, this Hypergraph Container Method, and show that it can be used algorithmically. And the type of applications we have are showing that problems are in some sense inherently easier when the inputs are nice in this symmetric sense. It's not having too large parts. We do leave more than a few problems. For example, just give some examples of how we use this, but I hope this is much more applications maybe in other areas of this specific area. So this is of course an interesting open problem. A more concrete open problem that was open and is left open is do we need assumptions. So now for k coloring, we said that if the graph is somewhat sparse, we have better algorithms. If the graph is somewhat dense, we have better algorithms. If the graph is somewhat regular, we have better algorithms. And we just remove all of these long list of assumptions and just get a better algorithm for take color and with no assumptions, maybe use these things you already have. Maybe even polynomial. So it would be better because it would also solve the such thing at the same time. It will be also fun. Yes, I will mention one quick thing before finishing. 2 weeks from now, I'm going to give a 2-hour talk about basically the same thing with IIS, but the talk is going to be much longer and much more technical. We are going to prove the graph container lemma, we are going to do some of the applications. So if anybody wants to consider going to there as well, then it's not exactly the same. Even though it seems like groups of people come here and they're quite disjoint, which is not good. So come there. Thank you. Yes.
So in order for the theorems of both, what are the nice properties?
So for the graph one, we stated them formally. The maximum degree is constant time average. For hypergraphs, it's going to be something similar, but not only about degrees, but also about coordinates. Something like the number of edges containing every vertex is constant factorial average one, but also something for pairs of vertices, and then pairs of vertices.